So let's see here. Sorry if you hear running upstairs. It's my kids making a racket. All right. So if we start with 21.42a, so we're starting it with cyclopentanone. And if we have a 1, 5, so 1, 2, 3, 4, 5. This is a 1, 5, 1, 5 dicarbonyl. Now we can't do an enolate because that can't do a conjugate addition. Can't. It will do conjugate addition plus it'll do 1,2 addition. So we have to mitigate the reactivity of that ketone or that enolate, right? So we're going to have to use the storic enamine synthesis for this one. So then the question becomes, well, what's my Michael acceptor going to be? Well, all you have to do is take the bits that are in the red circle and put them together to draw the correct alpha beta unsaturated ketone. So you can see that we have a carbon here, or a methyl group, we have an ether methyl group here, and 2 methyl groups here. So there's our starting materials, cyclopentanone and this alpha beta unsaturated ketone. So now to put the whole thing together, what we're going to do is we're going to take our ketone and we're going to form the enamine. So we're going to use dimethylamine. So dimethylamine and a catalytic amount of acid. And of course, we're going to remove water. And that's going to make the enamine. The second step is that we're going to treat it with our Michael acceptor. So I'm just going to move this guy up here. Okay. And that's going to produce the iminium ion and the enolate. And then in the last step, we hydrolyze the whole thing with aqueous acid. So H3O plus. All right. And you can put heat. It doesn't put heat in the book though. So we'll just leave it like that. And there we go. And that's going to give us our final product. The next one is a little more interesting because we didn't make a lot of, ethers in this class. But if you think about it, you could make that ether from an enolate, couldn't you? Right? If you had, something that looks like this. So if you had this enolate that looks like this, okay? Well, if you had this alkoxide, right, then you could just treat that with methyl iodide, and that would just, add to the oxygen, and the reaction would be done. So, that simplifies the problem a little bit. I'm going to erase that just in the interest of, real estate here. So, if we're starting it with cyclopentanone, we would want to deprotonate that completely, right? So it's going to react completely with this part of the molecule. And right, this part of the molecule is going to come from benzaldehyde. So our electrophile is going to be benzaldehyde, which has no alpha protons. And so what are we going to do? That means we're going to treat the ketone, the cyclopentanone, with LDA, which is going to deprotonate it completely. And then in the second step, we're going to put in benzaldehyde, right? So we're going to put in benzaldehyde. So what that's going to do is that's going to act as a nucleophile. We're going to get our nucleophilic attack like this. And let's just draw the intermediate that's going to be formed. So we're going to end up with this. So we have our aromatic ring here. All right. And then we have our alkoxide here. And so in the last step, we're going to treat it with methyl iodide. And that's going to act as a nucleophile. So we get nucleophilic attack, loss of leaving group, and that is going to give us the product like that. There we go. So that would be a directed aldol addition reaction. So for the first one, it's a storic enamine. So we'll write here storic, and this one here is a directed aldol reaction. All right, let's move on to the next one. It's 21.45. And this is just using that nuance that's shown in 21.7. So if we go back here, all the way back, okay, back, okay, it's using this reaction right here, where first we add a group to the beta carbon using conjugate addition. So we use a Gilman or a cuprate. And then to add the group at the alpha carbon, we use an alkyl halide. And so we use that strategy for both of these problems because we're adding groups at the alpha and the beta carbon of an unsaturated or an alpha beta unsaturated carbonyl. So for the first one, we're going to add this group first, right? So we need a methyl cuprate. So we're going to add, we can even draw the whole thing out here. We're going to start with our alpha beta unsaturated ketone. We're going to treat it with the methyl cuprate like this. And there's no mechanism shown for this in the textbook, but the intermediate you're going to end up with, like I showed you before, is going to be this enolate. So we have our methyl group installed, and now in the second step, we can treat it with our benzyl bromide or benzyl iodide, whatever. Let's choose bromide, it's more common. So benzyl bromide, and then we're going to get our nucleophilic attack and loss of leaving groups, kind of a funky arrow there, but anyhow, and that's going to give us our product for that one. In the second one, it's in the exact same vein, except for this one, we're going to start by adding the group at the beta carbon, which is a methyl. So we're going to use, I'll use my black pen. So we're going to use a methyl cuprate. So methyl cuprate, and that is going to give us this enolate. So we've got our methyl group here. We're going to have our double bond here and our alkoxide like this, okay? And the next step, we're going to treat it with methyl iodide. So that's going to do nucleophilic attack, loss of leaving group. So that's going to install the second alkyl group. So now we've got our methyl group at the beta, methyl group at the alpha, and we have an aldehyde. And if we want to reduce the aldehyde to an alcohol, we could use lithium aluminum hydride, or we could use sodium borohydride. We don't use that a lot in this class. And you could use water as a solvent for that. So there you go. So just one extra step, the reduction. Okay, let's look at 21.67. So I'm going to need a blank document to solve this one, so just bear with me. So this is question 21.67 from the textbook, so 21.67. And if we go over to the problem, let me make sure to read it exactly the way it's written in the textbook. So 21.67. It says, draw the condensation product expected when each of the following esters is treated with sodium methoxide followed by an acid workup. So the first ester they give us is this. So this would be ethyl pentanoate, or yeah, ethyl or ethyl valerate, either one. So we're going to treat this with sodium methoxide in the first step. And in the second step, we're going to treat it with aqueous acid. So this is going to be a Claisen condensation reaction, right? Claisen condensation. So let's see if we can draw a bit of a mechanism here. I just want to bring, there we go. All right, so what are we going to do? The first thing is we're going to deprotonate at the alpha position. So one of our ethoxides is going to strip off an alpha proton. So we're going to pull this off and make an enolate. So I'll draw the enolate down here. And it's not asking us to draw the mechanism, but I think it's good food for thought. I showed you the quick way to do this, but anyhow, let's just try it this way. So there's our enolate. So now this is going to react with the second molecule of the ester that hasn't been deprotonated. So we're going to have nucleophilic attack, right, like this, and we're going to form an alkoxide, and I'm going to need some more room here to draw that. So it's going to look like this. We'll draw our tetrahedral intermediate that's formed. So we have this, we have our alkoxide. I'll put that down here. Then we're going to have our ethoxy group here, and then we've also got 1, 2, 3, 4. So 1, 2, 3, 4 carbons like this. So then we're going to lose the ethoxide as a leaving group. And then it looks like you've got the final product, doesn't it? If you just draw this, it looks like you're done, right? You go and you draw this, you have your double bond here, and then you have 1, 2, 3, 4. But in fact, you're not done at this point, okay? This is going to be the final product, right? This will be the final product in the end. If you understand the mechanism, you understand that you're not done yet, because you still have ethoxide present in solution, right? And you have a very acidic proton in this molecule. Where is it? It's the proton between the two carbonyls. That thing is super acidic because when you abstract this, you end up with a doubly stabilized enolate. So I can even take this compound, probably, and just copy and paste it. Let's see if I can copy and paste it in here. No, that didn't work so well, but we'll give it a shot here. So we're going to end up with this. Let me just erase some of this spinach here. So what we end up with is this doubly stabilized enolate. And then after treatment with H3O+, and I'm sure I don't need to draw this mechanism, but I will. Okay, then you do a proton transfer. and that gives you the final product. So I can squeeze it in here. So our final product looks like this. So remember, the way I showed you how to do how to draw the product very quickly is you take the second molecule, okay, and you look at you've got the alpha and beta carbon. So all you have to do is make a connection. So between the alpha and beta carbon is between the alpha carbon and the carbonyl of the other ester. So you draw the carbonyl and you leave all of this out. So you just have 1, 2, 3, 4, and you're done. And that's the final product. Give me a thumbs up if you follow me on that one. Maybe we'll do the next one without drawing the mechanism. Okay, let's try one more where we don't draw the mechanism at all. See if I can do an even faster version of it. So this is 21.67b. So if you didn't understand my strategy, let me show it to you very quickly. So let me make sure I've got the right compound scribbled down. I do. So we're starting out with this ester. So let me draw the ester like this. So here is our ester. Okay, so here is our alpha carbon. If you draw a second molecule, so again, treating it with sodium methoxide, and you're treating it with aqueous acid in the end. So it's a Claisen reaction. So what you're going to do is if you just copy this part of the molecule, forget about the ethyl group or the ethyl part that's bonded to the sp3 hybridized oxygen. So if we copy, son of a gun, we copy this section. So copy and paste this section. Son of a gun. That didn't work at all. Okay, so let me redraw it. So what you're going to do is if you take the molecule and redraw it, all you're going to do is make a connection between the alpha carbon and this carbonyl. That's the answer. And you get rid of this. Okay, that's the whole answer. You just have to draw a little bit prettier than that. I would not accept that. Okay, so when you draw the final product, here's what it's going to look like. You draw the starting material with your ethyl group, your ethoxy group, and then you connect this to the carbonyl, and you've got a methylene and your phenyl, and you're done. Okay, does that help anybody? My kind of shortcut method for a Claisen? Yeah, one person likes it. All right, cool. Okay, a couple of people do. All right, so we said we were going to try 21.71 as well. So again, let me make sure I get the wording correctly here. So 21.71 says, draw the condensation product formed or obtained when the following compound is heated in the presence of aqueous sodium hydroxide. So we just have to figure this one out. I mean, it's an aldol condensation reaction, right? Because you're starting out with a carbonyl and you end up losing water. But let's just practice and see if we can figure out the mechanism. I like questions where you have to figure out a mechanism. I think those are kind of challenging and exciting. So 21.71, like this. And remember, in organic chemistry, the preferred ring that you're going to form in organic chemistry is always a 6-membered ring, right? 5-membered rings are also good too, but if you can ever form a 6-membered ring, that's what you're going to go with, right? So you can see that you've got alpha protons here, here, and here, right? There's 3 places that you have alpha protons, and it just says you're going to treat this with sodium hydroxide, okay? Sodium hydroxide. The problem with these 2 positions is if you were to form an enolate here, right, that would attack here, and you'd have 1, 2, 3, you'd have a 4-membered ring, okay? That is not preferred. Then if you abstracted a proton from here, right, then you'd have attack here, then you'd have 1, 2, 3, 4. Well, that's not good either, right? So if we pull off that alpha proton on the end, so if I was to pull off this proton here, so let me draw this proton, and if I draw a hydroxide ion, okay, and if it abstracts this proton, and we draw that enolate. So let's draw that enolate. It's going to look like this. Now, if this does a nucleophilic attack on the neighboring carbonyl, then you have 1, 2, 3, 4, 5, 6. A 6-membered ring is being formed. So this makes way more sense than anything else. Okay, so a handy way to redraw this actually is, I see my students do this sometimes, is to draw it like it's a 6-membered ring kind of thing. So what I mean is what I have drawn here, if you just change the conformation, you can draw it like this. So you go 1, 2, 3, 4, 5, 6, like that. And then you can kind of put your carbonyl here, just like a tiny little carbonyl, like that. Okay, so again, if we count our carbons, so I didn't put my enolate, so there we go. So if we count 1, 2, 3, 4, 5, 6. I don't know, sometimes students find this handy. You might not need to do that. You might be like, that's useless, but whatever. It's just something that students do sometimes. So then, oops, you draw your nucleophilic attack, and what you're going to end up with is something that looks like this. So you draw your 6-membered ring. This carbonyl is intact, and then you've got your oxygen with a negative charge, and then you have your aromatic ring. I'm just going to write pH there. Okay, so when the base abstracted a proton in the first step, what did it form? It formed water, right? So water is the conjugate acid of the hydroxide, so that's going to do a proton transfer here. So let's draw that product. So we end up with this, okay? But we know that what's going to drive this reaction forward is the formation of a conjugated system, right? So we're going to pull off the alpha proton, this alpha proton, so that means another ion of hydroxide is going to do a proton transfer here. So we have proton transfer like this, and we're going to end up with this enolate. So there we go, like that. And we have our hydroxyl group here, like this. Then we have our what's the word I'm looking for? Sorry, I put my bond in the wrong place, didn't I? Mr. Dion's getting a headache. All right, sorry. So we pull off the proton, we form the double bond, and we lose the hydroxyl like that. So that gives us our double bond like that, and that is going to be our final product. So there we go. So this is the final product, and that does have the molecular formula C12H12O. And then, of course, we lost the water in this part right here, right? You can see that we ended up losing a so let me circle it. We lost the proton plus the hydroxyl. So that is where our water molecule comes from. So there you go. So this is an aldol condensation reaction. So aldol condensation. And if you're wondering, well, why isn't this just an aldol addition reaction, right? Why didn't you just stop here? Well, the reason why is because this is going to end up losing water spontaneously. Like this step is definitely going to happen because if you draw out the full product, right? If we draw every single bond out, you can see that you end up with a fully conjugated system, right? So that's going to be the driving force in this reaction, that you make this fully conjugated system.